Okay, so Bishampayan Ghose, popularly known as BG to his friends, is the CTO slash co-founder at HelpShift Incorporation. BG is a career functional programmer, and he's got a wide exposure to a wide variety of languages and paradigms besides functional programming. He's an active member of the free and open source community, which most of us already are or are going to be part of very soon, I hope. And so amongst other things, he has contributed to projects including Clojure, Ubuntu, and Python and Django, naturally. He has more than a decade of experience in building medium and large-scale infrastructures. So, ladies and gentlemen, please welcome Bishampayan Ghose, popular in BG.
Check. Good morning, everyone. So, yeah, my name is BG, as Anuvrat said. It's a huge honor for me speaking here at PyCon today. The title of my talk, as you can see, it says the postmodern programmer. Okay, we kind of think of ourselves as modern programmers using modern programming languages like Python. The goal of my talk today is to take you beyond being modern. Okay, so let's start with the word definition of the word postmodern. What does it even mean? The word postmodern means going beyond modern. It means going beyond the status quo. The goal of this talk is to help people go beyond the general mindset around software development. And it's about developing a better understanding of the world that we are trying to model in our software. And of course, the goal is to develop better software, right? Okay. Before that, little bit about me. I consider myself as a software artisan. I express myself, my ideas through software that I write. I started with Python around 15 years ago in 2001. And of course, I've dabbled in many other programming languages since then. I've built a lot of systems. I've built transaction processing systems. I've built search engines. I've built distributed systems. And of course, I've learned a lot of lessons. I have committed a lot of mistakes myself. So this talk is sort of a gist of some of my lessons that I have learned in practice so that I can share it with you. Okay. So we'll start with a story. Okay. The story is based on my own personal experiences, but ultimately it's completely fictional. So no intention to cause any sort of libel. It's completely fictional, but the whole idea is to give you an analogy. So it's sort of an analogical, autobiographical analogy. That's how I call it. Okay. So we'll start. When I was a kid, I always wanted to build bridges. I was fascinated by very large buildings. I looked at bridges, large houses, factories, and I thought, hey, one day I would love to go and build them. Okay? And, you know, as children, we are very creative. We always think about building things. Children play with Lego blocks, for example. So you always think that when I grow up, I will not be playing with Lego, but I'll be building large buildings myself. So that's what I did. I went and started to learn, okay? But I was a naive child. I didn't have a lot of experience around buildings and structures and all those things. So I went and inspected some buildings on my own, and all I could see was bricks and mortar, right? And that's what I thought. I thought that bricks and mortar is all you need to build a bridge or a factory, right? I just need to learn how to use bricks. That's all I need. I don't need to learn anything else. If I just make myself a sort of an expert in laying bricks, I should be all set, right? So I used to think that give me enough cement and give me enough bricks and I'll rebuild the whole world. That's how I used to think. So I kept progressing in my craft. I became a professional bricklayer. Concrete, bricks, and plaster. That's what I would deal with every day. Okay? And I got really good at it. I would design bricks. I would lay them out in very beautiful patterns. I figured out pretty interesting ways of locking bricks together like Lego blocks. So improved bricks. I went into painting as well, painting of buildings. So I would build walls myself. I would plaster them, and I would paint them. Right? That was the fun. I mean, it was so exciting for me to be building walls and painting them and plastering them, all kinds of stuff. So it was amazing. Can people here please switch off the phones? Please put your phones on silent mode, okay? That's the least that you can do today. So yeah, I became a professional bricklayer, okay? I got awards in my field. I became a concrete mixing champ. I was an expert bricklayer. I was a fancy brick designer. I won awards for erecting the best walls around in my community, right? I was having fun, and I was really getting good at it, okay? Over time, I spent a lot of time just doing this. I kept building stuff using bricks and plaster. I would erect walls, just walls, nothing else, okay? Different types of walls, different sizes and shapes. I would experiment with mixing concrete in different ways to give it different properties. I would maybe even invent different kinds of concrete, right? But ultimately, I never got to build a bridge, okay? And that was sort of a huge frustration for me. I had spent a lifetime learning bricklaying, but I never got to learning architecture. You see, bricklaying is a very important step in building bridges. But as far as the path to building bridges is concerned, laying bricks is probably just the beginning of it. I mean, not even that. It fits somewhere in the middle. But that's not the be-all and end-all of building large structures. So years passed, and more than a decade later, epiphany struck me. I realized that bridges have got very little to do with bricks. Ultimately, bridge is a load-bearing structure. That's what it is fundamentally, right? Bricks sort of enable that. As a builder, I needed to understand the nature of the bridge first before I could even build it. It was less about bricks and concrete. It was more about load distribution. It was more about resistance to weather. It was about resistance to wind. I don't know how many of you have seen that Tacoma Narrows Bridge in the United States, which was built many years ago before we learned about civil engineering. And that bridge could not withstand wind coming in at a specific speed. And the whole bridge, even though it was made of concrete and steel, collapsed right away, right in front of people's eyes. One fine day, okay? That just happened. So I realized that, hey, architecture or building bricks is more about mathematics and physics than just cement and concrete and plaster, right? That was a big deal. I mean, that was a game changer for me. It opened my mind completely. I had found my calling, okay? And I went ahead from there. I was not stuck in just laying bricks. I went ahead. I learned about civil engineering. I learned about architecture. I learned mechanics. I learned a lot of different things. And finally, I got to do what I had wanted to do always. Okay? And I built bridges. Ultimately, I accomplished my life goals. I had taken the red pill, right? My worldview, my view about the world had changed completely. after I saw the big picture. Something that as a child I could not understand, because as a child I only saw bricks. But when I grew up, that's when I saw the bigger picture, and I realized the relationship between invisible things that play a huge role in the strength of a structure. That's the end of story. Okay? So as programmers, we are like that bricklayer. We have huge ambition of building large-scale software, but we are stuck in the small. Okay? We as programmers think that programming languages are all you need to learn to be able to build anything. If you know a language or two, like let's say one language for back-end, one language for front-end, and then you can go and build Facebook, but can you? You can't, right? We build many small things. We have so many projects on GitHub, small things that we do for fun, which is great in itself. But ultimately, those pieces of software are small and they are disjoint. They don't compose. I can't take two of my projects and create a third project, of course, because they are sort of standalone. And also to think of it from a different perspective, even though that kind of programming gives us a lot of joy, there is a lot of joy in reinventing the wheel. But are we having progress as professionals? Is our field having progress? Right? Reinventing another web framework. Where does it take us, really, honestly? Right? How many web frameworks do we have already? How many JSON parsers do we have? How many templating engines do we have? So that's like being stuck in the small. That's like exactly like thinking how that bricklayer was thinking about their art or their craft, right? And also, more importantly, whatever software we build, they are often very brittle, right? We write test cases, we do TDD, and we do lots of things, but they are very brittle. So one must ask this question. It begs the question that why is it so hard for us to build software? Forget about large-scale software. Even in the small, it's really hard to build software that we can guarantee will work as expected. Why do you think that is the case? Well, that's because programming languages distort reality. They show us a very idealized view of the world, which is far from reality. Okay? So inside a programming language, there is only one thread. There is only one computer. That one computer can never fail. If you set a variable, that variable will definitely get set, right? It cannot get unset, or it cannot be like half set within that program. Memory never gets corrupt. RAM is there. RAM is always there. Okay, whatever you set in memory, it's perfect. It will always be there, right? And I/O. Oh, I/O is not my problem. It's someone else's problem. It's the library's problem, or it is the operating system's problem. It's not my problem. It's the database's problem, right? Let's push everything to the database, right? Well, I think we need to realize that the world that we live in is not a program. It's a system, right? And by definition, it is distributed. Distributed systems are all around us. Each one of you here is a distributed system, right? Our human bodies are distributed systems. We have organs which have very specific purposes, but they work independently and autonomously without any central coordinator. No, the brain is not the central coordinator as we think. It does play a huge role, but it doesn't really tell or instruct your body to do each and everything. And of course, airline reservation, paying your bills, all of these things are distributed systems. Even organizing a conference. I'm sure it was not organized by a central committee where everything was, concrete instructions were given out by that one person to each and every executive. It didn't work like that. And many times people had to decide on their own. They had to make up on their own minds, right? So that is a distributed system. right? But how do you define a distributed system? What's the main difference between a distributed system and a program? I'll start with a quote. It's a very famous quote by one of the grandfathers of distributed systems, Leslie Lamport. He said that a distributed system is one in which the failure of a computer you did not even know existed can render your own computer unusable. Let that sink in for a moment. Right? It's like building a bridge where I don't even know that, okay, there are suspension cables, and there are thousands of them, and a cable that I did not know even existed, and that cable snapped and the whole bridge came down. That can happen, right? But more formally, what are the key differences, or how do you define a distributed system? Well, distributed system is a group of services that work together, okay? We do have sort of group of functions, let's say, in a program. But the key difference between functions in a program versus services in a distributed system is that there is no central coordinator, okay? So when you have hundreds of functions in your program, ultimately the runtime, the Python runtime, or the operating system is there to coordinate everything, right? So ultimately it's not really distributed in that sense. But in a distributed system, all these services, they work independently and autonomously. Of course, there can be coordination between them. There can be consensus between them. But these are not compulsory to have, okay? And as I said, no global supervisors. And of course, they are also connected. I mean, all these services, they're connected, but somehow. I mean, it's not really well defined how they are connected, right? How do they communicate with each other? It's not well defined. It's totally up to us to define how a system will communicate. And also, more importantly, the invariants, that is the things that never change, the invariants that we have in a single computer, they don't hold in a distributed system. As I said, right, for example, if you set a variable, it will definitely get set. That invariant does not hold if you are building or running a distributed system, okay? So the sad news here is that Santa Claus is not real, right? This is reality. The network is not reliable. We think that, oh, if I send a packet through a network, it will definitely get delivered, right? It's not reliable at all. Packets on a network can get dropped, they can get delayed, they can get reordered, they can get duplicated, right? Then, of course, we have other things which are like theorems and laws which we cannot work against. It's like trying to beat Newton's laws of physics. It's CAP theorem. So CAP theorem, I don't know how many of you have heard about CAP theorem. Okay, around 10%, which is great. I'll just give you a brief idea, very brief. I'll not go deep into it. But CAP theorem was a theorem that was discovered or invented by Eric Brewer. Eric Brewer is, again, a very well-known distributed systems professor. Now he works at Google. And the C, A, and P basically are three properties of any distributed system. The three guarantees that a distributed system can make, okay? So C stands for consistency. That basically means that when I read something from that system, when I ask the system for the value of, let's say, a variable or the status of something, it will always give me the latest value that it has seen, okay? I'm quoting latest because latest can be subjective, but in a global manner, globally latest, it should always show me. To give you an easier example to understand, let's say you write something to the database and you immediately read it from the database, okay? So whatever you wrote to the database, you should get it back right away. If you don't, then it's not consistent, okay? The second one is A, which stands for availability. So what does availability mean? It means that the system is always ready to accept reads and writes, okay? There is no condition where it can stop accepting reads or writes. Okay? And P is partition tolerance. So networks, as I said, are very, very unreliable. So if you have a distributed system, a network can get cut in half, where one half of the network knows about just a few nodes in that network, and another half knows about some other nodes. They don't know about each other's existence. That's a partition, and partitions happen in distributed systems and networks all the time. Okay? So partition tolerance is the property that you want a distributed system to have. It basically means that if a partition happens, and later when the partition somehow gets healed, there should be sort of consolidation between all the nodes in the system. Okay? So the system will automatically know what the consistent state should be, and it will fix the data skew if it has happened. So these are the three guarantees that a distributed system can hope to provide. So the CAP theorem basically says that you can only pick two. Okay? So you have to make a trade-off. So let's say I am building a distributed database. So of course I need partition tolerance. Okay? So that would mean that I have to choose either consistency or availability. There are different databases that fall on different ends of the CAP spectrum. Okay? For example, Cassandra is a AP system. That's what they call it. It's available and a partition tolerant system. It means that it's not consistent. So if you write something to Cassandra and if you try to read it immediately, you may not get the same data that you wrote. But eventually, it will consolidate. It will reconcile the differences in data. Okay? So it's an eventually consistent system. Okay? But important thing here is that we have to make these explicit trade-offs, right? It's not an artifact of some other process. We have to decide beforehand that, okay, I want this property out of my system, and I can trade off with that one. The other one is coordination problems. So let's say you have, again, a cluster with slaves and a master. Okay? So a partition happens, or let's say all the nodes join the cluster, and who becomes master now? Right? Who is the authority here? Or whose data is correct? Who should I even trust? Right? So this is a problem around building consensus. You need to have consensus, right? Let's say if we are voting on something, majority people should, whatever majority supports will get selected ultimately. That also can happen in case of distributed systems, where you need all the nodes to tell you that, okay, this is the value that I'm seeing, or this is the state that I have of the system in my database or my memory, and then later you can reconcile. Okay? But consensus building is really hard. It's really hard to build such algorithms. Of course, there are well-known algorithms, but they are also hard to implement. But the whole point here is that we have to, again, design very explicitly and think very clearly about these kind of systems. Clocks and time, right? We always think that, okay, our clocks can probably have wrong time, but computer clocks are always right. That's so false. It cannot be more false. In a system, if you depend on every node in your system having the right time, the exact same time, you cannot rely on that. Because clocks, not only do they skew, in the sense that not only do they over time build upon some difference in them, clocks can also go back in time. Clocks, we think that system clocks always keep on increasing. They are monotonic, right, in the sense that they are always increasing. But that's not true, because if you depend on NTP for your clock times, an adjustment can happen later, which will actually put your time back in time. Okay? And if that happens, imagine what can happen in a distributed system, right? If you're relying on time as being a sort of a very sacred thing. And of course, last but not the least, we have the Byzantine generals who will always come and screw things up for you. how many here have heard about the Byzantine generals problem? Okay, great. There is one enthusiast there. Great. So, again, Byzantine general problem was stated by Leslie Lamport many years ago. So the problem here is that you imagine a system where nodes, they send messages down the chain to other nodes, okay? And they will all trust the node that the message has come from, and they will just carry on whatever action or whatever variable value, I mean, whatever is there in that instruction, they will just blindly follow that. Now imagine a scenario where your nodes can actually lie to you. Okay, so nodes can send conflicting messages. So since it's a distributed system, every node is connected to every node. You can imagine something like that. So one node can receive a message saying that, okay, increment this variable, and the same node can receive another message from another node saying that decrement that variable. Right? And this kind of a problem can happen and does happen in distributed systems, and it's an incredibly hard problem to solve. Okay, to be able to sustain or sort of handle or deal with n node failures, or if you want to deal with n nodes lying to other nodes, you need to have at least 3n plus 1 nodes in the whole system. That's the minimum that you need. And on top of that, you have to also apply other algorithms for building consensus. Bitcoin technology, they have actually solved this problem in a very elegant way. I would highly recommend that you go and study how the blockchain works. That will give you a very good idea about how to build consensus in a distributed manner without any central coordinator. Okay? So these are like the problems that you face with distributed systems all the time, and I have not even scratched the surface here. Right? Over time, after dealing with so many failures and building such systems, I have learned some key lessons in distributed systems. So if I want to build a distributed system, what kind of guidelines can I follow? Number one, don't distribute, right? So if you can do without building a distributed system, by all means do that, right? Or use a third-party software which you think is completely reliable, which is rarely the case though, but still, avoid building a distributed system if you can. Avoid failures. You can also do that by having huge hardware resources, right? You can have, you can put the whole system into one machine. You can buy machines with 6 terabytes of RAM today, okay? 6 terabytes, that will cost you 100K USD, but you can still buy that one machine and run your whole cluster inside, and maybe have one more for backup. You could still do that, right? Put everything in memory of one machine. Third would be to accept failure. So it depends on how you define your service level agreements. There is no need to guarantee 99.999% uptime if you can't afford it. So advertise a lower uptime. And if that works for you, great. You don't have to work that hard to build a complex distributed system. Then would be redundancy. Have replicas and have more machines doing the same thing so that you can fail over very quickly if there are failures. More lessons. Divide and conquer, also known as sharding. Okay? If you can somehow partition your system into multiple independent parts, okay, then do that. If you can, let's say, somehow partition your data in such a way that all the data for a specific use case resides in one database, then you can split into multiple databases. It can be split geographically as well. For example, Facebook can't really afford to do that. But imagine a sort of a payroll company where there are offices in different geographies. So usually you may not need all the data to be available to everyone. So you can just partition the data and have different databases which hold subsets of the data. You can avoid coordination. You can, if your problem is such that you do not need coordination. To give you an example, if your database inserts are monotonic, in the sense that you only always update, you never, you only always add, and you never go and update some existing stuff, or you delete something, then you can avoid coordination by using special kinds of data structures called CRDTs, and there are other ways of doing it also. You can embrace immutability. Again, that also depends on your problem. You can build databases or systems which are immutable, where nothing really changes, but you just record new information. So that is also a very scalable thing. You can build such systems much more easily. Backpressure, something that's no one talks about, but very important, right? What is backpressure? Does anyone here know what backpressure means? Okay, I'll just give you a quick idea about that. So imagine a processing pipeline, right? A sort of data that goes through multiple processes, and ultimately, let's say it gets stored in the database, okay? Now, what will happen if your database is slow? Database is a little bit slow in accepting, in writing the data into the database. So what can happen? The processes that are further up the chain, they have no idea about that, right? They have no idea that the database is slow, so they will think that the database is just doing fine, so they will keep sending more and more data packets, and the database will get slower and slower over time, right? So what do you do in that case? Well, there are two ways of handling this kind of a situation. Well, the database can start dropping requests. That's possible. Database, if it can't cope up with something, just drop the packet on the floor. Another way would be to somehow propagate that pressure back up the chain so that the process that is producing the data stops, okay? Stops till the database sort of recovers, and then start sending it back again. How do we build such things? We build such things by adding a boundary to everything. For example, you add timeouts. You don't have basically unbounded of anything, okay? Everything has a bound. So if you're using a message queue, the message queue is not infinite. It will have a very fixed buffer size. If you're using REST calls or RPC calls, have timeouts there, and so on and so forth. There are other techniques as well. And of course, last but not the least, backup, right? We need to think about backup policies. Backups are not easy to make and also to reapply, but it's very essential. So that's something, again, that needs to be designed. It's sort of disaster recovery needs to be a part of our software design process. So programming languages are like bricks, right? They tackle problems at a very micro level. Of course, they are the building blocks, very, very important. You cannot do without them. But the focus area of a programming language is at a very small scale, okay? And of course, a programming language is completely unaware of higher level concerns. For example, the Python programming language or Java doesn't have any idea about cap theorem, right? Of course, it need not, because it operates at a very different level, right? But of course, we need better bricks as well. It's not just about learning architecture. It's not just about learning how to build bridges, but it's also about having better bricks. For example, there can be some key ideas in those bricks that can change the field completely. If I could build a brick which is sort of an arch-like shape, which becomes the keystone in an arch, that enables an entirely different kind of architecture, right? Compare that to bricks which are always of the same size and shape, then I can create a pyramid by stacking bricks on top of each other. But if I can get that keystone-like brick, then I can build a huge church, like something like this building, for example, which is quite lightweight. It's resting on pillars, right? But it doesn't have solid concrete walls everywhere, right? You don't need that, right? So we need better bricks as well. It's not just about learning the higher level ideas. It's not about learning about our world or distributed systems. It's about improving the building blocks as well. So how do we get towards better bricks? These are some of the things that are very essential. We need these things in our programming languages. Number one, immutable data structures. How many of you have been bitten by mutable data structures? Okay, quite a few people. Great. So for me, I'll tell you a story later maybe in detail, but very quickly, mutable data structures changed my life. So some bug happened in production because of that, and that changed my perspective about programming completely overnight. Okay, I used to take a lot of pride in being a good programmer, but then when I faced these kind of bugs, which had nothing to do with my program, but they had more to do with how different programs interact with each other, that's when I realized that you need immutable data structures in your programming language to be a better programmer. Functional programming, extremely important, and it's becoming more and more important today. Symbolic computation, right? Functional programming ideas are not new. They are very old, and they are becoming more and more relevant today, okay? Functional programming languages or functional programming ideas, they allow us to operate at a higher level of abstraction. And if we are able to do that, then we can somehow create a distance between the micro nature of computers to the higher level ideas that we want to ultimately express through our programming languages. And that opens up a huge possibility for optimization. Specifications and formal proofs. I want to be able to write proofs of my code. Okay? If I'm writing complicated distributed algorithms, then I must be able to prove my algorithms that they are correct. Because I can't do that while running it in production, because production I have other kinds of problems, right? So I need a way of specifying my programs. Just TDD or documentation is not going to be enough. Okay? Generative testing. There is a talk on generative testing tomorrow, I think, in Python. So what is generative testing? TDD or testing as we know today is called example-driven testing, where you basically write some examples and your functions are run over those examples, right? What if the examples that you have written are not right, they are not exhaustive? Imagine that you wrote a function to divide two numbers, and you wrote 10,000 test cases, but you did not check divide by 0. What will happen, right? Of course, you will have 100% test coverage, and you will have lots of tests. Your manager will be happy, but that doesn't solve the problem, right? What generative testing does is that it allows us to specify the input and output of our programs and the relationship between them. And then the test engine generates tests for us. I can ask it to generate 1,000,000 tests, and it will generate those 1,000,000 tests, and it will run those tests over your program. And if it finds an error, then it will shrink that data set back to the smallest possible input that will cause that bug. So it's a very important concept, and I would highly recommend that you learn about generative testing in Python. That will change how you think about testing in software. Better state management. So I was talking about mutable variables. You need mutation sometimes. Okay? If your programming language does not have mutation, then you will only end up heating up your CPU, and you will not have any output, because output means side effects, right? So we need a way of managing side effects in a controlled manner, so that we can reason about them, so that we can guarantee that certain bad things won't happen, right? So we need a better way of modeling and managing state in our programs. That will open up a huge array of opportunities in that programming language. Better state management will also give rise to better concurrency, okay? Languages that suffer from bad performance in multi-core and all of these things, they suffer because of lack of upfront design to enable concurrency, okay? And that's a price that you have to keep paying for it for many, many, many years, because these kind of mistakes cannot be fixed easily, okay? They have to be made and designed upfront. So we need better concurrency as well, because the whole world is concurrent, right? Like, I mean, we have a photographer taking photographs, but he's not asking everyone to just stop and so that he can take a photograph, right? It doesn't work like that. The world is distributed, and it's concurrent, and it's parallel, right? So this is the reality. So as programmers, we need to embrace reality and not create a fake sort of a silo where, you know, Santa Claus is real so that we can be happy, because that's not going to work. So we as programmers, we are very empowered, right? We are builders. We know how to build. We are highly privileged because knowing how to program is not really easy, okay? But we need to go further from there. We need to get out of our comfort zones. We need to be able to build better systems, right? And we need to shift our perspective from this idealized scenario to what it really is. So how do I get there? I have to learn how to read papers. There is no work, I mean, you cannot work around it. You have to learn how to read computer science papers, okay? That's the best way of learning about deeply technical matters, okay? Like cap theorem. There is no book on cap theorem. You have to go and read the paper, right? And of course, there are many blog posts and stuff, but ultimate authority would be that paper by Eric Brewer, right? We need to read code. I don't think we read enough code written by other people. Open up PostgreSQL and read PostgreSQL ka code, right? Learn exactly how MVCC works in that database. Maybe then you can steal that idea and implement it elsewhere, right? You can just do that. It's not a big deal. And of course, study other things beyond just programming. I mean, sure, Python 101 and all these courses are essential for anyone to get started. But once we get started, we have to think about having progress. We have to think about moving ahead in our journeys. And of course, we have to learn from history, right? People who do not know history are doomed to repeat it. So let's not repeat all the mistakes that have already been committed. Let's learn from history and, you know, don't just avoid these mistakes and just build better systems, okay? The time is now. Thank you very much. If there are any questions, I don't think we have enough time to answer them here, but please catch me. There's time? Okay, you want to waste some time. I got it. Okay, any questions? Anything? Ask me anything.
Okay, I'll ask one.
Yeah,
Distribute and
of course.
Okay.
So help shift, I don't want to talk about help shift here, okay? But yeah, we'll talk about it later. Of course, it's a distributed system. Yeah, so the question is, could I talk about formal proofs and specifications? They are two different things in the sense that specifications could be something slightly, it can have different concerns as well. So formal proofs, so there is this tool called TLA Plus. You should check it out. Again, invented by Leslie Lamport. So what it really allows you to do is to, so these formal proof systems, they have a language of their own, but it's a language to talk about other programs, okay? It's a program to talk about other programs. So in using that language, in that proof program, you basically talk about all the invariants of your system and how these subcomponents can interact between each other. And then you have a proof assistant, which is basically a theorem prover that runs on top of that proof, and it will basically tell you if there are any edge cases that you have not covered, or if your invariants do not hold under certain conditions. And specifications would be something like, okay, how can I, type systems you can think of as a very primitive way of specifying programs, but there are languages like Idris and Agda, and of course there are equivalents in Clojure where you can basically specify the input output of a function and the relationship between the input and the output, okay? So now once that specification has been done, it has various use cases. Of course it's used for testing whether you are invoking your functions correctly or not, but it can also generate test cases for you. Because the specification is an abstract specification, so you can generate test cases and you can generate documentation and all of these things.
Keeping all of these points in mind, which language would you say is the
I won't answer that here, but we can talk about it later. Yeah, no.
Um, So what I was asking was that, off late I've been looking at, as part of my job also, at things like Erlang, Elixir and all, right? So these have what they call as microprocessors or actor model, I think, based on the actor model perhaps.
Erlang is, yeah.
Yeah. So when I started learning about this stuff, I realized that actor model seems to be like the in thing, or is it like my
In thing.
perception is wrong, or is it like this particular model has
So,
a lot of advantages in concurrency? Is it?
right.
Okay.
So very good question. Anand's question basically is that actor models are very in things. They seem like fashionable today. So, but is it really that case, or is it about fashion, or are they fundamentally a very important part? So of course, computer science, our field is a very fashionable field, right? We are extremely fashionable. We follow fashion trends. That's true. But Erlang was written in 1984. So you can say that we are hipsters, that we like Erlang. So to answer the question, I think actor model is one way of modeling concurrency, because state is encapsulated inside the actor and you talk to actors through messages. That was also the core idea behind object-oriented programming, which has been completely bastardized and cannibalized by mainstream languages today. But the whole idea here is that state, or the mutation part of state, is never exposed to. We have audio problems here. So see, I think that's also a distributed system, right? A lot of failures today. Yeah, we have a backup. We just had a hot swap. So, yeah, so whole idea behind actor model is that state is encapsulated by the process. It's never exposed globally in any way, and you talk to the state, you mutate the state by sending messages to the process, right? So again, you will see that by definition, that solves some of the problems that we talked about, okay? Because the messages that are sent to a process, they are serialized. There are no parallel and concurrent writes happening on that so-called state that you have inside the process, right? And the writing is asynchronous, so on and so forth. So I think actor model, especially the actor model exposed by Erlang, is a very good way of modeling processes, but there could be other ways as well. Yeah, so Clojure as a language, a very good question. Clojure as a language actually gives you a whole toolbox for solving. So you can pick and choose depending on the problem that you have. So it's not like Erlang that there is only one way of doing it. Clojure has a very clear way of thinking about state management, and that sort of opens up a lot of opportunity for modeling different constructs in the same language without independent. Cool. Thank you, guys. If you have more questions, please catch me on the hallways today. Huh? Oh, okay. Yeah, I just opened my computer right now before giving the talk, and Apple Calendar just told me that tomorrow is Kenneth Golzanves's birthday. So I think it's a huge coincidence. Okay, so in the memory of Kenneth. Kenneth was a very good friend of mine and also a collaborator. So yeah, thanks, Kenneth.